Fernanda Andrade, and today I'll be talking about detecting non-interference violations with property-based testing. So this will be a bit challenging. We don't have these big rooms in Ecuador, and also John is here, so that will be a challenge for me. So I guess most of you know property-based testing, or not? Maybe can say who? Okay, great. So what is non-interference? It's just a cool name for a security property, and I will explain about that in a moment. So quick background about me. I'm the VP of engineering in a company called Stack Builders. We focus on functional programming. And because of that, I decided at some point recently to study formal methods, and I went to Spain to study in the software, and I had a really great experience working there in security and programming languages. So this is the result of that research internship. I'm professionally a Haskeller. I've been working with Haskell a few years, and now I'm living in Madrid, Spain. So let me start with an overview of what we'll be talking today. First, I talk about the motivation of this work. The goal here is not to go over the details or the verification or the property-based properties, but instead, the focus of this is to discuss some interesting ideas, and hopefully that will serve to inspire some people here. So we will be talking about non-interference, the proposal on how to test that with property-based testing, and finally some of the results that we got in this work. Okay, so motivation. As you know, security is very important, and that's the motivation. But information moves effortlessly through digital networks. Every day we use our phones or websites to access any information. The problem is that our systems are not secure. Information moves effortlessly through these networks. And of course, the loss of information is important, but also the financial and the damage to reputation. And we all know about all the vulnerabilities that have been found in the industry. And for instance, in this report from 2018, it was shown that 500 million customer data was lost. So even companies that are considered really big as Google, Equifax, eBay are vulnerable. So why these companies that have a lot of money are still struggling with that? It's clear that having the most clever people is not enough, and that's where we talk about the need for better tools. And in this area and in this conference, when we talk about better tools, we usually talk about verified tools, formal verified tools. And in particular today, I'll be talking about information flow control libraries. So what is information control in general as a concept? So information flow control is a security mechanism that ensures the secure handling of information, that ensures that information flows in a secure way through a system. And this system and security systems that are focused on information flow control do that by ensuring a property called non-interference. I'll be talking about that in a moment. So non-interference ensures that the modification of private data doesn't affect public data. So basically, if you have a system that handles public information as the weather and private information as credit card, basically that information, the credit card information doesn't affect public information. And this property, non-interference, is very important to ensure the security of information. And we talk about non-interference. Maybe this is new for some of you because this is a term that is usually used when we talk about formalizing mechanisms that use information flow control. So some of the information flow control mechanisms that you might know are some of these. For instance, JIT in Java, GSFlow, GSCode in JavaScript, or LIO and Mac in Haskell. So basically, these mechanisms restrict programmers from writing code that distribute sensitive data. So as long as developers use these tools and follow these tools, the information, the sensitive information won't be released. For instance, tools that, as I mentioned, these tools. And the important piece about these tools is that these have been formally verified. For instance, JIT was verified with Coq, LIO and Mac as well, the one with ACTA and the other with, and recently LIO has been even mechanized with Liquid Haskell. So this formal verification is essential to guarantee that these tools also are guaranteed that they are not leaking sensitive information. However, even though that's great, this formalizing a tool or a library is super hard. It takes a lot of time and effort in order to do that and being able to guarantee that a tool is correct. And for instance, in particular, a case that I want to discuss is LIO that was recently formalized with Liquid Haskell. It took 11 months just to formalize or to finish the mechanization of this tool. And actually running this mechanization takes 5 hours. So some of you are developers. Imagine having to wait 5 hours in order to find out there was an error or not. So it really takes a lot of effort to formalize that. And here's where we want to use property-based testing. If you have used it, maybe you know that tests can take just a few seconds to run. So here's where it's really great to use property-based testing because you can get results sooner and can help. Okay, so what was our proposal during this time in this work? First, as I mentioned, use property-based testing not as a way to replace formal verification, but a way to help the verification. That's the difference, and this is how it can help. So we were able to see that property-based testing helped us, and we did this with quick check to detect non-interference violations. And in order to do that, we used the meta theory. In order to test all this, we use an ongoing proof mechanization that was done in Liquid Haskell. So let me go and discuss about information flow control and non-interference again, because this will help us to understand how we can do that. So as I mentioned before, information flow control is about tracking and restricting how the information goes through a system. It's not about who accesses, but how the information flows through that system. So in order to do that, we do with 2 key aspects. We track the information, and we impose some restrictions and control over this information. And in order to do that, we use labels. Labels allow us to classify information, whether it's private or secret in some cases, but you can have different levels of information. So what is a security policy in this context? So basically, a security policy defines the relationship between the security labels. And for this, we use lattice. The use of this model comes from the 70s. And basically, these levels of information or these security levels are structured as partially ordered sets, where the order relationship specifies the security specify how these security levels are related. In a typical scenario, the security lattice consists of a two-point lattice, public, where we have two levels, public and secret. In this context, secret information can flow to public information. You can combine credit card information, credit card information and the weather information if you are working in the context of security. So you can have public information in secure information, but not the opposite. You cannot have secret information in public information. So that's how the information flows, from public to security, but secure information, but not the opposite. So as I mentioned, in a really common scenario, information can flow from public to secret, to secret to secret, to public, but not the other way around. That's how it's ordered, and that's how this order relationship is defined. So we mentioned that information flow control enforce non-interference, and non-interference is a property that ensures that this modification of data, the private information doesn't modify public information. And to understand non-interference, we need to review a concept that is called L equivalence. And in order to illustrate this, see this program with two labels. Here we have two levels information as well, secret and public. When we evaluate these programs, we apply operational semantics and we get another program. The output contains as well these two levels of information. And this is the initial part in order to talk about L equivalence. And formally, because we need to talk a little bit about formally, the input is a computation, is a program that is in the core calculus of the library with sigma, where sigma is the associated states and E is the expression. Then we evaluate using operational semantics and get this output. So I'll give you a quick example in a moment, but basically what is important here to understand is that the input is basically a lambda term. So our input is a lambda term, and that's what we will be using for our property-based testing. So a quick example on L equivalence. For instance, let's consider a credit card token is the secret information in the input, and this secret changes after evaluating to produce P1. However, for an attacker, which is an observer that can only see public information, you won't be see any change because this attacker can only see the public information. So for this attacker, this program hasn't changed. And there we can say that the input and the output are L equivalent. So now you know this concept, L equivalent. And basically it's the same as saying if we erase all protect data, the execution remains the same. Now that we know what this concept is, now we can talk a little bit more about non-interference. So there are several proposals to express what non-interference is, but this is just a general notion. So let's start with a program. This program, again, has the two levels, and if we erase all protected data in this first program, this program remains the same. And now we have another program that also does the same thing. So non-interference say that holds if two programs remain equivalent after each program from that is executed from the attacker perspective. That's saying if this is the same as saying that I have a program that is equivalent to another, and if we erase all the protect data in these two programs, both programs are the same for an attacker. So this is non-interference, and this is what we want to test with property-based testing. This is the property that we want to test. So just to finalize this, with these concepts, we have the actual testing workflow. Our workflow begins by using the meta language. Since we are using Liquid Haskell, we have access to the meta language immediately. So we have the Haskell program and the SAT that comes from the mechanization with Liquid Haskell. So we use this meta language to actually generate programs, to generate Lambda terms. So with using the meta language, we generate Lambda terms that will help us to actually test whether these programs remain equivalent after evaluating these programs. And in order to evaluate these programs, we create an interpreter because we are in the meta language level. And with this, we can see that the non-interference property holds or not. And this can pinpoint exactly an error in the Haskell library. So we go from the meta language, from the Lambda terms to the actual library. So what were our results? So actually we were able to test and they were catching errors that we added manually. But during this process, we found that actually some errors in the implementation using property-based testing. So thanks to the property-based testing, we found issues in the implementation of this mechanization. And as I mentioned before, instead of waiting for hours, with property-based testing, we just only had to wait 15, up until 1 second. So that was great. That helped us a lot. So in order to finish, 2 points that you need to remember. Information flow control libraries. If you are programmers, you want to test this because this is the only way to actually guarantee. It doesn't matter how smart we are, you need the only way to say that a system is secure is by using these verified tools. And second, if you are interested in more theory, so basically property-based testing can work with the meta theory in order to find discrepancies between implementation and the actual meta theory. So it's a way to bridge these two worlds. Thank you very much. If you have, I don't know if I have time for questions, but.
So, any questions, observations?
Thank you for the talk. One of the public information that's, or the public data that is always, or almost always available is the runtime of the change running on the secret.
Sorry, there was some noise I couldn't hear. Can you repeat again?
So one of the public information that you have as an attacker often is the runtime of changing on working on a secret. Do these tools help you give guarantees that the runtime is always the same, or?
No. These tools are actually focused on the implementation, on the logic of the library, not in the like the time that they are running.
Yeah. So, okay. So that's a class of information leak that you still need to solve. Otherwise, do you have any suggestions on how to help that? Yeah.
I'm not sure. I'm not an expert on that area, but I think right now the importance is to focus that the actual logic that you're writing, the implementation of what you are doing, is secure. And
yeah.
That's the hardest problem. So
yeah, but even from the same notion of security, like it's not secure if I can tell from giving from the
execution time.
From the execution time whether I'm getting close or something. Like I could create an oracle on the secrets and extract the secrets that way.
Yeah. In that case, this tool doesn't cover that.
Yeah.
Just going to follow up and say the classic solution to that is to use a constant time algorithm, of course. So if you've got a constant time algorithm, then there's no side channel attack. So that's one solution. The other solution that people commonly use is to put obstacles in the way of extracting the timing data. So if you can perturb the timing loop in some way, or you make it sufficiently imprecise, then you can't actually detect the difference between the different algorithms. But you then need to start to think about statistical timing properties, because even statistical timing can perhaps give you some information.
Good. Thanks very much. And let's thank our speaker again. Thank you.